We will now ask the question of whether a multivariable function is differentiable. Intuitively, we can say that a multivariable function is differentiable if it is locally linear at that point, but I would like to express this as a limit definition like we did in single variable calculus. So here we say that the function f of xy is differentiable at a point x0, y0 if the limit as h goes to 0, except for this h is going to be a vector. Okay, so we can think about that as the vector h1, h2 going to 0. Okay, so that's going to be the limit of f of x0 plus h1, y0 plus h2. So we're going to add a little bit to both x and y. We're going to subtract f of x0, y0. That kind of looks the same. Okay, but we're going to have a difference here. We're going to subtract the gradient of f at x0, y0 dotted with the vector h. And then we're going to look at that limit all over the magnitude of h. And if that limit is 0, we say that the function is differentiable. Now that seems a little bit mysterious. Okay, I have some things that look familiar. Here I have some stuff that looks like it's part of the difference quotient. Okay, but then I have this gradient over here, and I'm not sure why that is there. Okay, and then I'm dividing by h. That's something that I had before. Okay, but this whole limit is going to be 0. It's not actually going to be the derivative. So I kind of want to figure this out here. Why is this the case? Well, let's think about that single variable definition. So in fact, what I'm going to do is I'm going to convert this to a single variable definition. So I'm going to do f of x plus h minus f of x. Okay, and then I'm going to do minus f prime of x. So instead of the gradient, I'm just going to have f prime of x. Okay, I'm going to have some x zeros here. And then instead of dotted with h, I'm going to multiply that by h. Okay, so I'm going to have the absolute value of that all over the absolute value of h. And then I'm going to start dividing some things by h. So this is the limit as h goes to 0 of f of x0 plus h minus f of x0 all divided by h. And then when I divide f prime of x0 times h by h, I just get minus f prime of x0. Okay, so I'm looking at this single variable definition, and I'm saying now, if this limit is 0, the derivative exists. Well, what's happening is I'm comparing the difference quotient here with the derivative. And instead of saying that the limit of the difference quotient is equal to the derivative, I'm going to look at the difference between this difference quotient and the derivative. And if in the limit it's 0, then these two things are going to be equal. So what this definition is doing is it's not saying that the limit of the difference quotient is the derivative. It's saying that the distance between the difference quotient and the derivative goes to 0 as h goes to 0. And that's essentially the same thing. So above, what I have here is that I'm looking at the difference quotient, okay, and I'm comparing it with the derivative. And I'm saying if the difference between the difference quotient and the derivative is 0, then it's differentiable. So here, this is in some sense the derivative. And so you can see why this definition of differentiability is equivalent to our definition that we had in single variable calculus. Okay, so then now the question becomes, are particular functions differentiable? How do we show that a function is or is not differentiable? So I'm going to look at a function, the square root of x squared plus y squared, and I'm going to ask myself, is that function differentiable? Okay, so let's see. We need to first find the gradient in order to figure this out. Okay, so we're going to find the x derivative, which in this case is going to be, and I'm going to find these derivatives, okay, using the definition. Okay, so I'm going to say that the x derivative of this is going to be the limit as h goes to 0 of f of x plus h. So in particular, we're interested in knowing this derivative near 0, 0. So I want the partial derivative at 0, 0. Okay, that's going to be the limit as h goes to 0 of f of 0 plus h. So this will be h squared plus 0 squared minus f of 0, 0, which is 0. And then I'm going to divide that whole thing by h. Okay, so the partial derivative of this function with respect to x at 0, 0 is equal to 1. Okay, if I had just used the derivative rule here, I would not have been able to see that the partial derivative there is actually equal to 1. Okay, but using the definition, I can do that. Okay, so let's remember that this, in some sense, this is going to be f of 0 plus h 0 minus f of 0, 0. Okay. Now, I'm going to do the same thing for y. So the y derivative at 0, 0, using the definition, is the limit as h goes to 0. Okay, this will be the square root of 0 squared plus h squared. Okay, so now we're doing f of 0, h. Okay, minus f of 0, 0 is 0. Then we're going to divide that by h. And that limit is going to be 1. Okay, so both the partial derivatives, okay, at 0, 0 exist, and they're both equal to 1. So now I want to apply that definition with the gradient. So we're going to do the limit as absolute value of h goes to 0. Okay, so that's the length of h going to 0. Okay, in fact, I believe that I missed this length of h there. Okay, so here, when I'm applying that definition, okay, this absolute value sign is standing for length or magnitude of that vector. Otherwise, I can't really take the limit. Okay, so we're going to take the limit as the absolute value of h goes to 0, okay, of, okay, f of 0 plus h, 0 plus h, so f of h, h. So this is going to be the square root, it's going to be the square root of h1 squared plus h2 squared, a minus, and now we're going to take the vector 1, 1, and we're going to dot it with h1, h2. And then we're going to divide that by the length of h, which is the square root of h1 squared plus h2 squared. Okay, so what we're going to get here is square root of h1 squared plus h2 squared minus h1 minus h2 we're going to divide that whole thing by the square root of h1 plus h2 squared. Now, we're taking the limit as the length of h goes to 0. And this limit, in fact, is not going to exist. So if we investigate that limit further, it's actually not going to exist. So because that limit does not exist, then this function is not differentiable at 0, 0. Okay, so I actually had partial derivatives here. Okay, I was able to show what the partial derivatives are. Okay, but in fact, even though I had those partial derivatives, this function turns out not to be differentiable at the point 0, 0. Okay. Now, let's take this a little bit further. Do another example. Okay, so here I've got the function x to the 1/3, y to the 1/3. Okay, I'm going to do the same thing. So the x derivative at 0, 0 is going to be the limit as the length of h, limit as h goes to 0 of, okay, so this will be h to the 1/3 times 0 to the 1/3 minus f of 0, 0, so that's 0, divided by h. And you can see that that limit's clearly 0. And then when I want to find the y derivative at 0, 0, okay, that's going to be 0 times, it's going to be the limit as h goes to 0 of 0 times h to the 1/3 minus 0 all over h. And that, of course, is also going to be 0. So the partial derivatives here both exist, and they're both 0. Okay, so now if I take the limit as the absolute value of h goes to 0 of f of xy, what am I going to get? Well, that's going to be the limit as the length of h goes to 0 of h to the 1/3, h1 to the 1/3, h2 to the 1/3, minus our gradient, which was 0, 0, dotted with h1, h2. And then divide that by the length, which is the square root of h1 to the 1/3 plus h1 squared plus h2 squared. Okay, so here, this piece is 0. Okay, so now we're looking at the limit of h to the 1/3, h2 to the 1/3 divided by the length of h1 squared plus h2 squared. Okay, again, you can show that that limit does not exist. Okay, so neither one of these functions is differentiable, even though the partial derivatives we saw existed, at least if we were using the limit definition. Okay, so let's look at what the pictures of these functions look like. Okay, so first, the square root of x squared plus y squared. Okay, notice that you get this kind of bowl shape, but it has a tip at the bottom there. Okay, and you can kind of remember from your intuition about differentiability of single variable functions if you had these jagged edges. Okay, so things like the absolute value function, okay, or these cusps that the derivative did not exist. So here at that point right there at 0, 0, if you're looking at that point, it's just not going to be locally linear at that point. If we zoomed in on it, it's still going to look like a pointed surface there. Okay, so it's not going to be locally linear. Okay, so it makes sense that the derivative at 0, 0 doesn't exist. Now, if we look at x to the 1/3, y to the 1/3, okay, so we kind of zoom in and look around. Okay, so if you're kind of spinning this around and looking at it, it seems like this surface like has some sort of tear or something right at 0, 0. Okay, so here we expect the top to come together from one diagonal and another diagonal. We expect those to come together in at a positive number. Okay, but if you kind of flip it in this direction, you expect these kind of lower valleys to come together at 0, 0. And so it seems like there's kind of this tear in this surface. Okay, and so here, again, the partial derivative does not exist. Okay, so going back to our examples, there is a theorem. The theorem says, if the partial derivatives of f exist and are continuous, and that is so important, and are continuous at the point P, then the function f is differentiable at that point. So here, in our previous examples, the partial derivatives exist. Okay, so here we had the partial derivatives existed. We had to use the definition to see that, but the partial derivatives exist. Okay, but if we were to use the formulas to compute the partial derivatives, we'll see that they are not continuous at 0, 0. Okay, so for both of these functions, the partial derivatives exist, but they're not continuous at 0, 0. And so that gives you an indication of why these functions are not differentiable. That does not prove that they're not differentiable, but it gives you an indication. Okay, but there's a theorem that says that the partial derivatives of f, if they exist and are continuous, then the function is differentiable. Okay, so we can look at a function like, say, f of xy equals x times sine of xy, and we can ask, is that function differentiable? Okay, and we can figure that out. Okay, so we can compute the partial derivatives with respect to x and y using the product rule. The partial derivative with respect to x, okay, so I have a first part there and a second part there, okay, is the derivative is 1 times sine of xy plus, and now I'm going to have the x left alone. The derivative of sine of xy is cosine of xy, and I take the derivative of the inside with respect to x, and so I'm going to get y. Okay, so that's the derivative of f with respect to x. And then the derivative of f with respect to y, okay, it's a little bit easier. Okay, it's going to be x times derivative of sine is cosine of xy, and then the derivative of the xy is in fact just going to be x, so I'll have like an x squared there. Okay, and you'll notice, okay, that both of these, both partials exist and are continuous. Okay, it doesn't matter what the x and y are for all xy. Okay. Okay, so now we've shown that the function is differentiable. And then it says find the linearization, or find the equation for the tangent plane. Okay, so, or find the linear approximation. Okay, so here we need that f of 1 pi over 2, okay, that's going to equal, in this case, it's going to be 1 times the sine of pi over 2. Okay, so that's 1. And then what is the gradient of f at 1 and pi over 2? Okay, so let's plug in 1 and pi over 2. So sine of pi over 2 is going to be 1. And then I'm going to get a cosine of pi over 2 in the next term, which is going to be 0. So I'm going to get 1. And then the df dy has a cosine of pi over 2 in it. So that's going to give me a 0. Okay, so the gradient there is 1, 0. So we can say that f of xy in this case, okay, is approximately, well, f of 1 pi over 2, which is 1, plus, okay, the gradient, which is 1, 0, dotted with, okay, x minus 1, y minus pi over 2. Okay, so the linearization here is going to be 1 plus x minus 1. In fact, the linearization is just going to be x. Okay, so near the point 1 pi over 2, this function, x times sine of xy, is approximately just x.